Okay, and welcome to the last section of Chapter 10. We're just going to be taking a little bit more of a dive into vector fields here. So here you can see your generic vector field here. So it takes 3 inputs from R3 to R3. It'll take 3 inputs and give me 3 outputs. And that's because it maps a vector to a vector. So our first example we're going to look at is the planar vector field. Planar because it's mapping R2 to R2. So it's a plane to a plane. It's going to have 2 inputs and 2 outputs. In this case, the outputs are constant. Do you see that? So no matter what x or y I put in, I'm getting an output of 1 in the x direction, an output of 0 in the y direction. That's why they're calling this a constant eastward wind. Okay, so basically no matter what, at each point in my field, here I'll put a little sketch here. So here's my plane. And at each point in the plane, I'm going to draw the vector 1, 0, which looks exactly like this. And this is my constant eastward wind. Or if you want to think about it, with the wheat analogy, a vector field is talking about the entire stock of wheat in the presence of a wind, I suppose. So you can imagine a field of wheat, we're viewing it from above. If we have a constant eastward wind, then the field of wheat will look exactly like this vector field. Okay, so that's my version of drawing it, but we can just swing down a bit and see how the computer would draw one of these. No surprise there. Constant vector field, eastern wind. Okay, so in general, how are we going to draw a vector field? Well, we're just going to pick a point and evaluate the vector at that point, and that's going to give us a vector, right? So think about the piece of wheat up from the ground. There's some velocity from the wind. It's pushing the wheat in a direction. How do we know what that velocity is? That's precisely this vector. You have to evaluate at the specific point to get the velocity of the wind or the shape of the vector. Okay, so here we're just going to look at this exercise really quick, 10.4.1. Think of a map of the world with a large Category 5 hurricane present in the South Atlantic. Draw a vector field that describes the wind motion would look like in that case. Sure, so let's send ourselves to the South Atlantic. I'm just going to keep myself on a plane, and I've got North America over here on the left-hand side, Europe over there, Africa, South America. So the South Atlantic's going to be right there. All right, so now we know where the South Atlantic is. Let's clear that up. Draw a vector field. It's a hurricane. South Atlantic. Let's think about the Coriolis effect. I don't really know which direction they're supposed to rotate in. I'm going to go with this direction. Talk to a meteorologist. They'll tell you what the actual direction this is supposed to rotate in. It's going to look like. All right, so if it's a hurricane, we all know that near the eye of the storm, the vector field actually becomes 0. And then it probably grows, and then it probably dies really quickly outside of the storm itself. So then maybe you just have like some random winds out here. Right. Just based on the rest of the world. But we definitely have that vortex-looking shape in the middle. So there's our hurricane. All right, let's look at another example. This one's called line source. What does that mean? This means that there's the word source has a very specific meaning when it comes to vector fields. And line just describes the shape of that source. So a source, when we're talking about vector fields, a source is a place where vectors seem to exit from. Okay, and this is just in quotes, right? Seem to exit from. They don't necessarily have to be exiting from the source, like not causally linked, but it looks like it. It's observed to be that case. In this case, it's saying the shape of that source is a line. So let's scroll down. This is what the vector field is defined as. It's just this x plus y in both directions. But let's scroll down and see what it looks like and see if we can find that line source. All right. So here's our vector field. And I think you can all tell that there's this line right here that it looks like a bunch of these vectors are exiting from, right? They're all like kind of emanating from this line. So in this case, what is that line when it comes to the x, y plane? That's the line y equals negative x. We're going to notice, if I plug it into the top here, y equals negative x right up top here, we see that the vector field on, I'm going to call this x comma negative x, that would be letting y equal negative x, equals x minus x, x minus x. This is the vector 0. So it's saying on this line, we have the vector 0. That's not going to guarantee a sink or a source. Doesn't guarantee, spelled that wrong, a source. but it's necessary for a source. So it's not a sufficient condition, but it's a necessary condition for a source. So we see that here. Let's just verify at one other point that this vector field was actually computed correctly. So let's grab this point here. This is the point 2, 7, it looks like. 2, 7. What should the vector look like at 2, 7? Vector should be 9, 9, which is up and right. Is that vector up and right? It looks like it was scaled down a fair bit, but yeah, that should be the vector 9, 9, but it's definitely up and right in the correct direction. So yes, this was drawn correctly. My cat wants to join again. All right, let's look at a vortex. This would be more akin to what we were saying with our hurricane, because what's actually going to be happening here is that this is saying that, for example, let's grab a couple points. Let's grab like 1/2. Let's grab 1, 1 actually. Look at the point 1, 1. That's going to emanate, the wind direction at that point is 1, -1. Maybe we look at v of 1, -1. The wind direction at that point is the y value goes in the top, the x value goes negative, and in the bottom, I get -1, -1. V at maybe -1, 1. It's going to give me the y value goes up top, the negative x value goes in the bottom. And so we see, let's just plot this out really quick before we look at the answer. A couple of these places. So 1, 1, to me right there, says my vector goes to the right by 1 and down by 1. So to the right and down points in that direction. At 1, -1, which I guess is 1, -1's down here, I go -1, -1, so I go left by 1 and down by 1, so that's over here. At -1, 1, that's over here and up there. I go up and to the right, and I'm sure over here, I'm going to go up there as well. If I connect these all together, I'm probably going to get something that looks like that. So that's the idea with the vortex. We should see, I guess, a clockwise rotation about the origin in our answer when we scroll down. Let's see if we did that right. And there you have it, clockwise rotation of the origin. One last thing I'm going to talk about in this section, it's a pretty quick section, is what we call the vector field algebra. So this idea of algebra, what does it actually mean in math? We're just going to see what operations are valid on vector fields. Okay, can I add them? Can I subtract them? Can I multiply them, etc.? And adding them is not really too bad, right? So adding two vectors, bam, we defined it right there. All we're going to do, this is so component-wise, f1, f2, f3 is in the first vector, g1, g2, g3 is in the second. We're just going to add these like we would add vectors. Okay, so I don't think that's a surprise to anybody here that we can add vector fields together, and we just add them component-wise. And we can look at an example on these. Okay, so if we look at the vector field x, x, and the vector field y, y, then in the first case it only cares about the x coordinate, the second case it only cares about the y coordinate. Let's see what those look like. Yeah, so you can see basically these are more of these line sources, right? So this is a line source in the vertical direction and a line source in the horizontal direction. And they have their specific directions outside of there. But we can add these together, and we should notice, where do pieces add together? So we notice in the upper right quadrant they should add together, but in the upper left quadrant these should cancel because they're actually opposites of one another. So I should say this is, maybe I'll call this negative, positive, call this one, this is positive, positive. Maybe over here we'll call this, these should add together, this is positive, positive, and these should be opposites. This is negative, negative. So what should we see when we add these all together is we should see extra directions in the top right and bottom left, and then they should cancel in the top left and bottom right. So let's check and see if that actually happens when we scroll down. And look at that. So they've canceled, not completely in the top left and bottom right, but they definitely cancel along that line, y equals negative x, and then they're definitely adding in the top right and bottom left. So that's what happens when we add them together. Okay, so there's another thing we can do, and that's scale. Scale by scalars, that's what we call them, scalars. So we can scale a vector field by scalars, not so much of a surprise there, but the extra thing is that more than scalars, we can actually scale by scalar fields, right? That's actually kind of the reason why we'll call these scalar fields. So if f is a scalar field, then it can scale, ta-da, a vector field. So that's kind of the last little bit we want to think about when it comes to this this vector field algebra. All right, that's all I have. Thank you very much.